Welcome to the EPG Pathashala, the lecture series in computer science for the postgraduate program, and this is the compiler design course and 24th module where we will discuss about the 3-address code, the semantic rules for generating 3-address code for arrays and Boolean expressions. So, the objectives of this module are to learn to write semantic rules for arrays to generate 3-address code and to learn to write 3-address code for Boolean expressions. So, this is about it. So, we have looked at the grammar for arrays. So, S produces L colon equal to E produces E plus E or E. Now, this E can be again E star E or minus E or whatever it is. So, whatever we know as expression, that can be adopted here also. And E produces L, and then L produces E list followed by close parenthesis. Then I have L produces ID, and then I have E list produces E list comma E, and then E list produces ID followed by open square brackets E. Now, this variable L is used to indicate it is array variable. Now, E also produces L. So, the LHS and the RHS both can be arrays, that is I can say x of I is equal to y of g, that is also a possibility. So, this grammar supports that, and not only that, here this is a Pascal syntax. So, therefore, when I have E list comma E, so I can have multi dimensions with a comma separating the dimensions, and everything is put into a single square brackets. So, as against C where you have A of I comma j as A of I followed by j, you have it in two parentheses. Rather than that, here it is going to be A of I comma j, which is the Pascal syntax. So, whatever is applicable here can be extended to C also. Okay. Only thing is the way in which you write the grammar is going to be different, but other than that it is going to be the same manner in which you are trying to write it. So, we have seen that the array variable has two attributes. One is the place, which is a pointer to a symbol table, and the other is going to be offset, which is going to be used to move through the array index. And this is your recursive equation, which is going to be used by the array for generating your 3-address code. So, EM is equal to EM minus 1 plus IM, where M here refers to the dimension, and E1 is equal to I1. So, that is when you have only one dimension, it is the same. Now, the function that is going to be used by the array for generating 3-address codes are elist.endim, so which is going to be returning the number of dimensions in the elist. So, how many dimensions are available based on the comma. So, as and when I encounter a comma, because in the grammar there is a comma elist comma E, right. So, as and when I encounter a comma, I am going to increase the number of dimensions by 1. And then the next function is called as limit. It takes two arguments, one is array comma j, which is it returns the nj number of elements in the jth dimension of the array. So, the array will be referred to as the parent using a name, and then the j means the second dimension, for example say. So, if I say array comma 2, meaning that the second dimension, how many elements are there, will be returned by what is the number of elements, that is what is the definition of the number of elements as per the input, that will be returned by this function limit. So, limit array comma j basically returns what is the dimension of the, what is the number of elements of the jth dimension of the array. Okay. So, that is what the function limit returns. In elist.place, it is it can hold the value temporarily from an index expression. Let us take this, we have already seen this also, but let us just take a quick look on this. This is the row major information. So, I have array 1 to 2, 1 to 3, okay, which means it has got a dimension of 2 cross 3, okay, of integer. So, this is how it is defined in Pascal. So, A of I comma j is what I have here. So, base address is calculated, base address of the array A plus I1 minus low 1 into N2 plus I2 minus low 2 into W, and that is equal to, I am rearranging this, I1 into N2 plus I2 into W plus C. Now, what is C? C is nothing but which is done during runtime. C is equal to base address minus low 1 into N2 plus low 2 this into W. Okay. Now, here in our context, low 1 is 1, okay, I am starting with 1, and low 2 is also 1. It starts again with the index 1, and the number of elements of the second dimension is 3, and width is 4 because it is an integer array. So, how do I compute this? This is nothing but 1 into 3 plus 1 multiplied by 4. So, 1 into 3 is 3 plus 1 4 into 4 16, that should be subtracted from the base address, and finally it should be incorporated here for computation. Okay. So, in our case you will basically do this example I into 3. If I have to compute some location's address, so I that is used here, I into 3, that should be added with I2, so T1 plus J. This is multiplied by W, that is what we are doing here, plus this constant C. So, that constant C is indicated as T2 of T3, that is from the base address you shift so many bytes. Okay. That is what this basically does. So, this has been now converted to a recursive expression, that is what we have already seen, and this recursive expression is incorporated in the semantic rules of generating 3 address code for arrays. So, let us look at it sequentially. I have also added inference here because this is very difficult to comprehend. Say for example, you have S produces L colon, this is your first production, S produces L colon equal to E. Now, what am I checking here? If L dot offset is equal to null, because we already said L is an array variable, and this L also produces ID, a simple ID, or it could be an array itself. So, if its offset is null, which means that L refers to a simple variable or simple identifier only. In that case, you have to emit L dot place is equal to E dot place. On the other hand, if L has an offset which is being computed, then you emit L dot place of L dot offset is equal to E dot place. Okay, so this is a 3 address code which is being generated. Either if it is an identifier, you simply emit, for example, here ID is equal to some expression, ID is equal to A plus B, whatever it is, I can basically emit that. Here if it is an array, if the LHS is an array, then I will use that as a basis for generating my 3 address code. So, that is what we have inferred here. The second production is E produces L. Okay. Again, whatever we have done for the LHS here, that has to be carried out for the RHS. So, E produces L is here. So, the RHS L is checked for whether it is offset is null or not null. If the offset is null, you simply emit E dot place is equal to L dot place. If the offset is not null, which means it is an array, in that case LHS variable will be declaring as a new temporary variable, and then you emit E dot place is equal to L dot place of L dot offset. So, whatever we have done here, the reverse is done here, but the LHS can be a new temp has to be created if it is going to be an array on the RHS. So, that is what we have done here, otherwise it is the same as the previous case only. And then these are pertaining to arrays. Okay, the first and the second are pertaining to arrays. Now, these two are the same as the previously looked upon expressions semantic rule, that is have E will be E dot place is equal to new temp, and then I will say emit E dot place is equal to E1 dot place plus E2 dot place. Similarly, for parenthesis, it is simply E dot place is equal to E1 dot place, which is the same as already discussed values only. Now, here this is the closing scenario of the array. But before we look at this, let us look at this L produces ID, which is a simple one. So, L dot place is equal to ID dot place, meaning that it is a simple identifier, it is not an array. So, I will simply say L dot place is equal to ID dot place, and in that case I will say L dot offset is equal to null. So, we have already seen in the previous slide itself that if offset is null, it is referring to a simple identifier. It is not an array, that is what we have already done, and that is done with respect to this semantic rule in mind. Okay. Now, this one is L produces E list close parenthesis. Now, once I see this production, it means that my array is over. Okay, my array is over, which means it has to look at the last computation of the RHS and put it into LHS. So, what I will do here is L dot place is equal to new temp, and I also say L dot offset is equal to new temp. Now I will emit, I know C, it is base address minus that computation, low 1 into I1, which is done during runtime. So I will emit here L dot place of C comma E list dot array. Now this is referring to an array, right? That array place is available here. Now this is what we said, array refers to the address of the base array which is referred to. Okay, so this refers to the address. And L dot offset is equal to E list dot place multiplied by width of E list dot array. So this is also computed. So this array will have a place and that has got a width. Okay, width returns the size of the integer elements. Okay, so that is multiplied and given as offset here. Okay, so the next this is a core thing where we are incrementing the number of dimensions also. So when I encounter a comma, I am going to say the number of dimensions is going to be incremented by 1. So what I do here is I create a new temporary variable first, and then I say m is equal to the dimension of this plus 1. That is, E list 1 have come up with so much of dimensions there. Okay, that is, it could be I am in the middle of nowhere. So to start with, this will be 0. So my number of dimension will be 0 there in that case. So it will be plus 1. So I will say m is equal to 1. I am incrementing the number of dimensions. And then I emit E list 1 dot place multiplied by limit of E list 1 dot array comma m. So what will limit return? Limit returns the dimension size of the mth dimension, that is the number of elements of the mth dimension. So supposing I am declaring an array of 2 comma 3, this m will be 2. Okay, I mean this will return 2. Okay, so if I am referring to the first dimension, m will return, this limit function will return 2. So I will multiply the place with this 2, which is already a new temp, okay, and then use that. Then I will emit t is equal to t plus e dot place. So I will increment that, okay, and then E list dot array. Now this array refers to, this is the same array referred by E list 1 also. I am just assigning it here, saying that both refers to the same array only. And then I will increment E list dot place is equal to t. I will assign that, and then I will say E list dot endem is equal to m. Now this is necessary because subsequent calls has to use this value of m for number of dimensions. Okay, that is being computed here as an increment value of 1. So that will be used in subsequent reductions. So let us, the last one is this one where I have E list produces id followed by open parenthesis e. So in this case E list dot array will be id dot, that is the base address, id dot place, and E list dot place will be e dot place referred to by e, and E list dot end dimension is equal to 1. So this is where it starts 1. And the previous one, if you could remember, E list dot endem is incremented by 1. So you start with a default number of dimensions as 1 here, and that gets incremented in the previous calls. So the C of E list dot array returns the base address of the array, and E list dot place returns the dimension of the array. That is also done here. Okay. So with reference to this, these are your semantic rules. Now with the semantic rule in mind, let us consider this example where I have a 10 cross 20 array. So the first dimension is of size 10, second dimension is of size 20, and then w is equal to 4. Width is a 4 because I am looking at an integer array here, and let us say you have to compute this assignment, x is equal to a of y comma z. Y comma z I do not know now, that will be called by the programmer. So I can say a of 4 comma 3. Okay, how do I compute the address of a of 4 comma 3 is what I have to basically look at. So what I should do is 4 comma 3 should be referenced with respect to 10 in an array of size 10 cross 20. I have to go there directly and fetch it. Okay, that is assigned to x. This has been done in one shot. So how do I do that? So let us say I have x is equal to a of y comma z. So this is your first production. Then I have L produces id. Then I have E produces L, and then I have L produces E list close parenthesis. Then this E list is E list 1 comma E, and then the E list 1 is id of open parenthesis E. Now this is this id is capital A. This is this E corresponds to Y. This corresponds to Z, and I have a closed dimension here. and this corresponds to this corresponds to X, and this corresponds to E produces L, okay. This ID corresponds to capital A. So, A here, this corresponds to Y, this corresponds to Z, and this corresponds to X. So, this is my sequence of derivation. So, what will I apply first? I have to apply this rule first, okay. LHS there is no problem because it has got no offset, it has got only the value. So, L dot place will be equal to E dot place only, but I have to compute E dot place. To compute E dot place, this L has an offset. So, how do I know that? I have to start from here, okay. If you have a derivation tree in mind, so this is going to be where we are going to start with. So, to start with, this is the first application of rule. I will look at the first dimension. So, T1 will be equal to Y into 20. So, here I have Y and compute it. So, I have to look at this production here. So, I look at this production here. So, I will compute this. So, this will be used for computing. So, with that in mind, if you could get your next steps listed out, we know that this is the sequence of productions which we have already seen, and the rules application will be first computing Y into 20 because I have to refer to A of Y comma Z. Now, I know T1 is there, okay. Then I have to add with that Z, okay. T1 A of Y comma Z means I have to look at Y rows, Zth column, okay. So, I have to complete Y minus 1 rows and then go to the Yth row, that is what is done here, and number of columns is 20 because 10 rows and 20 columns is your array size, okay. So, T1 plus Z, so I am incrementing that, and then T2 is equal to C. Now, this is your base address. So, base address we already know how to compute, which is nothing but base minus low into, it depends upon the number of dimensions of n1, n2 and the low 1 and low 2. So, it is nothing but base minus low 1 into n2 plus low 2 into W. So, that is what is done here, and then I say T3 is equal to 4 into T1. So, this 4 into T1 is nothing but computing the width I have to shift. This is your offset computation here. T3 is equal to 4 into T1, which is the offset computation, and then I will say T4 is equal to T2 of T3, okay. T4 is your new temp, T2 is the base address computed, and then T3 is the offset. So, T4 is A of Y comma Z, that has to be assigned to X, and that is what we have done here. So, this will be the sequence of steps. So, you start applying it as a derivation tree, and then if you could keep working the tree from the leaf towards the root, you will be in position to get the same result. So, this is how the sequence basically goes. I have to first compute Y into 20, that will be added with T1, okay, and I will use the base address as C, and then I have to multiply T1 with 4, that is the offset computation, and then I have to shift L dot place of L dot offset, put it in a new temporary variable. So, this corresponds to here E produces L, okay. So, this L has now one offset. So, I am computing L dot place of L dot offset and then assigning it to the LHS non-terminal. Now, in addition to that, we have already seen type conversions and type checking. Now, the code, tree address code itself can incorporate type conversions, okay. For example, here E dot type is equal to, if E1 dot type is equal to int and E2 dot type is equal to int, then this is int, else it is real, is what we have basically arrived at here. So, how do I compute the code here? E dot place is equal to new temp, which is the same, and I will check the validity of this condition here, and if this is true, I will simply say do an integer addition, okay, do an integer addition. I can handle the other cases similarly, okay, I can handle else if using a sequence of else if and if. I can basically generate the other possibilities of type conversions also. I will do a real addition, if one is int and other is real, I can do that. That is, I am combining type conversions with reference to in the context of tree address code generation itself, because that is also semantic rule, this is also semantic rule. So, we can just integrate them into a single semantic rule, which is going to do a type checking as well as tree address code generation. Both are possible. Now, the next programming construct which is normally encountered is Boolean expressions. So, Boolean expressions are part of the conditional statements, the if condition or the loop construct which is while or the for, etc. So, Boolean expressions computes logical values. It is used for flow of control statements. The Boolean operators are typically and, or and not. And you can also combine them using relational operators less than, greater than, less than or equal to, greater than or equal to, equality and not equal to. Okay. Now, let us look at the syntax directed translation for this. Okay, this is just one way. We will be revising on Boolean expressions in multiple ways as and when we encounter. So, this syntax is similar to normal expression only, but we will evaluate this using the OR operator. When I say an OR here, I am emitting 3 address code. I am computing A or B, I am computing B or C, whatever it is. Okay. So, E dot place is equal to new temp, emit E dot place is equal to E1 dot place or E2 dot place. Similarly, for this production is going to be nothing but replacing that with and, here is nothing but replacing this with not. And if it is a parenthesis here, I have E dot place is equal to E1 dot place, which is going to simply prioritize the execution of E1. Okay. Now, this is typically going to be part of your Boolean expression. Now, I am going to use a function called as next state, which is going to be referring to the statement number of the current statement. Okay. And then when I say a plus 3, it basically tells me that increment 3 and go to that and generate a number here. Okay. So, next state is going to generate the current line number, and plus 3 will be current line number plus 3. So, here next state means current line number, plus 2 means adding to the current line number. So, I will typically encounter ID1 relop ID. Relop is a relational operator. So, I can say A less than B, that could be a simple RHS. In that case, how is my 3 address code going to look like? So, LHS will be an E dot place is equal to new temp. We already know that all my 3 address codes, you can have only 3 addresses, okay, at the most. And here I have here ID1 dot place is one address, ID2 dot place is another address, and this is the address which I am going to go to. Okay. So, I have 3 addresses here to handle this, and this is the conditional jump if x less than y go to some label L1. Okay. Now, these 5 statements will be generated as 3 address code for this particular piece of expression. So, I have E dot place is equal to new temp, and in that the first emit is this one, followed by this, followed by this and followed by this. So, 4 statements will be generated as part of the 3 address code corresponding to one relop. Okay. And then I have E produces true. E produces true will be the final termination. In that case, I will generate emit E dot place is equal to 1, and false will be emit E dot place is equal to 0. Okay, there is a typo here. E dot place is equal to 0. Let us take this example, A less than B or C less than D and E less than F. So, we know that and is done before OR. Okay. You do and has more precedence compared to OR. So, how will the expression be? It will be E1 or E2, and then this E2 is now replaced as E2 and E3. Okay. So, I will evaluate this first and then I will evaluate E1. Now, in this example, okay, in this example, I will first evaluate C less than D and E less than F, both are expressions. Now, this will be fitting into as ID1 relop ID2, again one more ID1 relop ID2. So, I will generate 4 statements for this and this, connect them using AND. That is a very simple task, simply saying a temporary place is equal to this one and this one. Finally, 4 statements will be generated as part of this A less than B. This will be again referring to a single place. The ANDed one will be in a single place. I can do an ORing of that, which is again a simple expression. So, this is what is going to happen. So, let us look at this. So, the first one is, what is my first statement as part of the 3 address code ID1 relop ID2. If ID1 relop ID2, go to next state plus 3, that is your first statement. So, I have the line number as 100 which is available here. So, I will say next state will return 100. So, 100 plus 3 is 103. Next is what? Temporary variable T1, that is equal to 0. And then I have a go to of next state plus 2. This is my next state here, plus 2. And then I have to generate T1 is equal to 1. Okay. Which means that if you look at these 4 lines, if this is true, I go to 103, meaning that I am setting my temporary variable to 1. If this is false, I am coming here, which means that my temporary variable is set to 0 and I do a go to 1, that is I am skipping the statement in that case. Okay. And then again for C less than D, because we know that A less than B or C less than D and E less than F. So, I am not concatenating it together. I have to do C less than D and E less than F first, followed by I have to OR it with A less than B. So, A less than B result is available in T1. Okay. This has to be definitely done. So, if C less than D, go to 107, T2 0, again go to 108, T2 is equal to 1. Similarly, if E is less than F, go to 111, T3 is 0, go to 112, T5 is equal to 1. Okay. So, what have we done? T1, T2 and T3 both all has basically been set to 0 or 1 here, and therefore, they correspond to the individual expressions. So, now T4 is equal to T2 and T3. I am doing an AND first. I am doing an AND first, and then T5 is equal to T1 or T4. Okay. T5 is equal to T1 or T4. Then the next, the shorthand version of this Boolean expression is called as short circuit code, where 3 address code can be generated without generating the complete expression itself. That is, if in the AND, if one of them is false, I need not even evaluate the other expression. Similarly, if in an OR, if one of them is true, I need not evaluate the other expression at all. So, that is short circuit code, which we will incorporate, and that prevents us from evaluating the complete expression. So, that we will see in the next modules. So, to summarize this module, we have looked at 3 address code for arrays, 3 address code for Boolean expressions, and an introduction to short circuit code. And with that, we wind up this module. Thank you.